So let's look at another example of using function pointers. The specific example is going to be doing integration of a function of a single variable. So let me explain what that means. Let's take a look at the following. So I'm going to draw an axis. So here's going to be my y-axis, and this is going to be my x-axis. So this is x, and this is y. So if I have some function, let's say y is equal to x squared, right? And we write as y is equal to some f of x. What does that mean exactly, y is equal to f of x? It means if you give me an x, I'll show you y. So in this case, if x is 0, so y is 0. If x is 1 squared, so it's over here. And if x is 2 squared is 4, so it's going to be sort of over here. And x is 3 squared is 9, so it's going to be over here. So that's the familiar parabola that you learned in high school. Okay, so that's an example. That's what we mean by a function of a single variable. A single variable is called x. Another example of such a function is, let's say y is equal to some function of x, and let's say it's equal to 1. Okay, what does that mean exactly? It's a function of x. For every x you give me, I will find a y. For every value on this line, I will find how high I'm going to go. So what does it mean f of x is equal to 1? It means that no matter where you are on the x-axis, y will always be equal to 1. That's a constant function, right? Y is equal to 1. So a problem that we have in many, many cases is if I give you some function, I want to know the area under the curve, under the function that's drawn out on an axis. So for example, if I say I want to know the value of the function, the area under the curve of y equals 1 from x equals 1 to, say, x equals 2, so we can figure that directly without any fancy stuff because, well, this is a square, right? Because the function is always, the value of the function is 1 no matter where you go. And from here to here is also 1, so the area of the square is 1 times 1, so the area is equal to 1. So if I want to do that, that's pretty straightforward. But we want to be able to solve this thing for some general term functions. Let's say I have a function that sort of looks like this, function sort of looks like that. And I tell you I want to know the value under the curve from, say, positions x equals 1 to x equals 2. That's a different story, right? This is that's not so well behaved. How do we figure this thing out? So in contradistinction from the previous example, where we could find an exact value for the area, we just multiplied the base times the height. There are certain cases where it's not even possible. So for example, let's say this is x equals 1. And what I do is I draw a half a circle. So I draw half a circle with a radius 1, and this would be the rest of the circle. Excuse the artwork. So the area of the whole circle, since the radius is 1, so the area would be pi times the radius squared. But the radius is 1, so it's going to be pi times 1 squared, which is pi. That would be for the whole circle. For half the circle, of course, it can be pi over 2. But since pi is an irrational number, pi over 2 is also irrational, which means that there's no finite representation. There's no way to get an exact value for pi. The decimal expansion goes on forever and it doesn't repeat. So for some, as we saw with the square, I can find that exactly. For some, I can't. What we'd like is some way of getting an approximation for sort of an arbitrary function of a single variable. So it turns out not to be that difficult, right? So let's say I have some function looks like that, let's say. And I want to know what's the area under this under the curve for the function, say from some value of x equals a to a value for, say, x equals b, right? I want the area under this curve. So one way to do this is a very clever idea. Simply you decide what would be the height. Say, for example, over here. The height over here would be f of a. That's the definition of this diagram here. So I define some interval here on the x-axis. Let's call that interval delta x. So if I draw a rectangle of size where the length of the interval is delta x, and the height over here is f of a, so f of a, which is the height, times the width, delta x, gives me the area of this particular rectangle. If I move over to the next position, right, that's going to be a plus delta x, or a plus delta. I just call this thing delta instead of delta x. It's going to be easier, right? So let's call it delta. So it's a plus delta. So the area of this rectangle over here is going to be the height, which is going to be f of a plus delta, right? F of that x times, again, times delta. And then I move it over again. So that's going to be f of a plus 2 delta, right? That's going to be this x over here is going to be, this is a, and this a plus delta. This is going to be a plus 2 delta, right? And so the height is going to be f of a plus 2 delta times delta is going to give me the area of the next rectangle. Now you'll notice, of course, that I'm going to, if I want to use this, and it goes all the way across to B. If I want to use this as a approximation for the area under the curve, the problem is I'm going to end up underestimating because of these loose spaces, right? Especially if the curve grows quickly. But if you think about it just a little bit, it becomes clear that if you make delta smaller, then the lost area is going to be smaller as well. And if you make delta really, really, really small, then you can get the lost area to be really, really, really small, right? So that is the idea. What you do is you make these various rectangles going from A to B with a very small base, very small delta, and you add them all up, and that's an approximation for the area. That process is useful in so many areas. It's very difficult to even overstate the importance of it, and it has a name. That process is called integration. And in math, usually you use that symbol for integration. You have if I have some function f, so I say I'm going to integrate the function f of x. Why is it called integration? Because you're integrating all these things. You're summing them off. You're adding them all together. And you say I'm going from a to b. This is called a definite integral of f of x, a to b. So how would you actually write a program to do this? Well, it's pretty straightforward. Let's see, for example, for some specific function f of x, right? So let's say what I want to do is I have, let's say I have f of x equals x squared, right? That sort of parabola over there. And I want to go from a to b, right? I want to go from a to b. And I want the area under the parabola. So the area, so f of x is equal to x squared, right? That's a parabola. And so I could do it like this. Here's my function, integrate. Integrate. Now, integrate is going to take a and b. A and b are going to be doubles. So I say double a, and I say double b. And it's going to return, of course, a double, right? I'm gonna add up all those rectangles and return a double. So it's pretty straightforward. How do I do this? How do I do this? So what I'm going to do is I'm going to have some double. Let's call it S for sum, which I initialize to 0. And what I'm going to do is I'm going to generate these rectangles, and I'm going to add them up into S. So let's set a delta. Delta is also going to be a double. And so let's say delta is going to be delta. Let's make it pretty small. Let's say 0, 0, 0, 1. That's going to be my delta. And I'm going to have a double x that tells me where I am on the x-axis, right? X is going to tell me I'm over here. And I'm going to start x at a, right? So x is going to start out at a. And I'm going to have a while loop, right? And my while loop is going to say, while x, which starts at a, is going to be less than b, I'm going to generate a rectangle and add it in. So what I'm going to do is I'm going to say sum, s, plus equals, right? Into sum, I want you to keep adding in what? The function, I'm going to multiply the base times the height. So the base is going to be delta, right? That's going to be the base. And what's the height going to be? Well, it's going to be the function at x. Well, since we're looking at a parabola, f of x equals x squared, so it's delta times x times x. And we keep adding it in, and we're going to say, we're going to move x over, so x is equal to x plus delta. X is equal to x plus delta. So we get a new value of x each time as we move it around, and we're going to add in the delta. Delta stays the same, it's the base, times x squared. We're going to move x over and so on, and we're going to keep doing this until x, as long as x is less than b. The reason we don't test for equality, why don't we do a for loop, or something like that, or a while loop, and say, keep doing it as long as x is not equal to b, because when you're dealing with floating point numbers, with doubles, it's almost impossible. It's almost impossible that you're going to get an exact match. So this is the very simple thing. When you come out of the while loop in S, you have the sum, you have that integral, and then you simply return S, right? And that's the whole function, right? So again, you set S to 0, you set delta to some small value, you set x at the beginning, and you keep moving x each time. So you have delta times the function at x, which is x times x. Then x moves over, it's x, it's the current value of x plus the delta. And you keep doing it as long as x is in the range. And then when you're finished, you come out and you return. So that's very straightforward. But now this is such a nice function. We like to be able to use this the same idea if I have, let's say, x cubed. So I'd have to write another function, right? I have to write another function for x cubed, and that will be, everything will be the same, except instead of saying x squared, it's going to have to say something like x times x times x, right? And that, I have to write a whole new function for that. Or if I want, let's say, if I want sine of x, right? So it's going to be delta times some sine of x, And so every function that I want to get the integral for, I'm going to have to write another integrate function. That seems like a lot of work. If the whole thing stays the same, except for the function, wouldn't it be a nice idea if I could do something like this, right? If I can have another parameter in here, right over here, where I pass in the function that I want to integrate. Let's say some f is going to be the function, and then I simply say f of x, where f is the function I pass in, if somehow I can pass in a function. And if you think about it, that's exactly what we can do with these function pointers, because we can actually now pass functions to other functions. So let's go back to the class notes. Here is how we might do it. We want to be able to write a function, let's say integrate. Here's the function integrate, just like we did before, except it's different than the previous one, because now instead of just taking a double of these, we were integrating from a to b, we're also going to take a function, a name of a function, and now this is going to be, of course, much more general. I no longer have to write an integrate function for x squared, for x cubed, for sine, for anything else. If I can pass in the function, integrate will do it for me. The only thing is, there's no such thing as a general function in terms of a parameter. I have to define what kind of function it is that I'm passing in. And what I want to pass in is a function of a single variable. So what I want is that this type, func, is going to be a type that is a function of a single variable. So that's what we do over here. Let's take a look at this type def. So what we're defining is func, right? We're going to define what is func. So if we get rid of the type def, we saw func becomes the name of a function. It's a specific function that takes a double, because a pointer to a function is the same as the function. A pointer to a double and returns a double. That's a function. But once I put a type def in there, then what does func become? Well, let's use the right-left rule. So we say func is. Let's say func is what? Well, func is a. Let me go this way. Func is a pointer to a, hit the parentheses. Func is a pointer to a function that takes a double, I hit this, and returns a double. Again, I start at what would have been a variable name, right? Because all the others are not. All the others are either types or things built into the language, right? Double is a type, parentheses, stars, they all belong to the language. Double is a type, parentheses here. So the only thing that's not is func, right? So func is what's being defined. So again, func is a pointer to a function, right, that takes a double and returns a double. So what's examples of something that takes a function that takes a double and returns a double? What's some examples of those? Because I now have a new type called func. Well, let's take a look at this. How about the function line? Is line a func? Can I take the name line and pass it into functions that require a parameter of type func? Right? And the answer is yes. Why? Because what is this? Line is a function that takes a double and returns a double. How about, and what does that function do? This is equivalent to the function y is equal to x, right? F of x equals equals x, right? What is that? That's like this line, right? What about the other one? What about square? Well, square a func? In other words, can I take the name square and pass it in as a parameter as a value for a parameter that requires a func? Of course, right? Because y, square is a function that takes a double and returns a double. It happens to calculate y equals x squared, right? What about cube? Yeah, of course, right? Because it takes a double, returns. So this all examples of funcs. So now I can use this. I can have now one function called integrate. And that's what we want over here. One function called integrate that takes 3 parameters, right? It takes 3 arguments. The first argument will be a function pointer. In other words, the name of a function, of special functions, right? Functions that take a single double, return a double. I can't pass, for example, a function that takes 3 integers and a bool, because it's not of type func. Func requires a double as in and a double as out. So integrate now, I'll be able to pass it a function name and a start value for the x and an end value for the x, and it's going to integrate. How would I use something like this? So here's an example of a main function. I can do this. I can say the integral of f of x equal x between 1 and 5 is, and I just call the integrate function. So what am I passing in? I'm passing in 3 arguments. The first is the function name, and I want to integrate from 1 to 5. And over here, the value of f of x equals x cubed. I call the function integrate, but pass the function name cube. Why? Because that's a func, and the integrate function requires a func, and again, from 1 to 5. So this is really a very, very nice idea. How does integrate work? Well, we just saw on the previous video, and I'm going to ask you to code this thing up as an assignment. It's really straightforward. I just want to make sure you see by actually coding it up and running it how this thing works.